Okay, so taking us to the finish line, Charles Gammie, on the status of the Blandford-Znajek effect.
Yeah, so I'm going to be talking about the Blandford-Znajek effect. I'm going to review what the Blandford-Znajek effect is. Then I'm going to talk about what predictions that it makes for possible observations, and then prospects for testing the predictions observationally. And before I go into that, let me just say thank you to ITC. ITC didn't exist when I was here. It was 10 years in the future. So it was so long ago that Avi was a shy assistant professor, and Daniel Eisenstein was a graduate student, as was Elliot Quadier. I worked in Ramesh's group, and it was a very exciting time. Just to address some of the comments about risk-taking in academia, we were really encouraged to take what I thought were pretty big intellectual risks at that time, and run with it. So thank you in particular to Ramesh. I also want to mention that it was a time of great uncertainty, as it is for all postdocs and graduate students. You know, we didn't know what was going to happen. So it was a group that included Eve Ostreicher and Elliot and others. So my heart goes out to younger people who are still, making their way through the system. So I'm going to talk about one object here, really, which is M87, which is what's shown up here. This is a Hubble image, and prospects for testing Blandford-Znajek in the context of M87. So just to remind you of some of the basics. So I'm going to use A to denote the dimensionless spin here, there's a theorem in classical general relativity due to Hawking, which says that the area of a event horizon has to increase, and that leads to the notion of an irreducible mass of a black hole. So it's the mass of a black hole which has the same horizon area as a spinning black hole. And I've provided an expression for this here. So the larger the spin, the larger the difference between the mass and the irreducible mass, which means that there's a free energy associated with the spin of the black hole, which is the difference between the mass and the irreducible mass. To lowest order in the spin, that's proportional to the square of the spin divided by 8 times the rest mass energy of the black hole. And this is really quite a bit of energy. So if I've done my sums correctly, it's of order 10 to the 61 ergs for a 10 to the 8 solar mass black hole with maximal spin. And that's about 10 to the 20 solar luminosity years. So it's really potentially an enormous store of energy. All right, so can we get energy from a rotating black hole? So of course, this is a storied history in the sort of golden age of relativistic astrophysics from the late 60s to the early 70s. Penrose wrote this famous paper in the late 60s saying that it's possible to split a particle very close to the event horizon of a rotating black hole and send one particle in with negative energy, which is how we manage this trick, and send the other particle out with larger energy. Soon afterwards, Bardeen wrote a paper which said that if you take a thin disk and build up the mass of a black hole through accretion from a thin disk, then the black hole will spin up, and it'll spin all the way to spin 1. And so that excited people's interest in rotating black holes in an astrophysical context. Then along came Bardeen, Press, and Tucholsky in the early 70s and said, this Penrose idea is great, but it's going to be hard to turn this into industrial scale production of energy from a rotating black hole. And then at the same time, there was work going on pulsars, which was closely linked to work on rotating black holes, and in particular, Goldreich and Julian developed their force-free model of a neutron star magnetosphere. And they showed that you could get energy out of an aligned dipole, which was different from what people expected based on a vacuum dipole model, which people had worked on up to that point. So this is sort of the context for Blandford-Znajek's work, which came out in '77. And they applied several of these ideas in their calculation. But the core of this calculation was just to find a solution for the electromagnetic field structure around a rotating black hole, and to show that that leads to extraction of rotational energy. And this is a long, difficult paper, but the outcome is pretty simple. You apply Maxwell's equations, you apply conservation of energy and momentum, and you assume that there's not much plasma around, but it's enough to make E plus V cross B is equal to 0. And then you apply some boundary conditions and you get a solution for the magnetic field structure around a rotating black hole in the low spin limit. And it's pretty simple. This bit here, this is the radial magnetic field in this monopole model that they put in the paper. Just drops off as 1 on r squared. So it's you can imagine that there's a monopole of one sign in one hemisphere and the other sign in the other hemisphere. Nothing happens to the theta component of the magnetic field at lowest order in the spin. And then there's a azimuthal or toroidal component of the magnetic field, which is driven by frame dragging. And this component is proportional to the spin plus higher order corrections. Okay, so you can see that this produces kind of a swept back configuration for the magnetic field. If you start out with sort of a porcupine, you spin up the black hole, and then the porcupine gets turned into kind of a spiral. And that situation leads to outflow of both angular momentum and energy. And it's really not that different from what happens if you have a star with an embedded magnetic field and you spin it. And it has a trailing spiral pattern in the magnetic field around it, and it drives outflow of angular momentum and energy. So once you know this, and all this is in a particular coordinate system, mind you, you can calculate the Blandford-Znajek power of the black hole. And again, to lowest order in spin, it scales as the square of the spin multiplied by the field strength on the horizon squared, and then some other dimensional pieces to make the dimensions come out right. Okay, and we now see this effect in numerical simulations, as Asaf mentioned in his talk. So this is one of our current simulations. This color shows the logarithm of the density here, and the black hole is over here. The spin axis is on the left side, and this material here is orbiting around the black hole. This is a simulation that we've run on Frontier, thanks to the work of Ben Prather, who used to be in my group. And you can see that there's high density in the midplane here of the region around the black hole, and there's low density up here over the poles of the black hole. And if you'll excuse my crude graphics, there's magnetic field in that region, and it's got an approximately monopolar configuration, and you can time average this and show that it matches up to the Blandford-Znajek solution. So this Blandford-Znajek solution arises naturally in numerical simulations of accretion onto black holes. And I'll show you a slightly more dramatic view of this. It comes from a movie that my former student George Wong made. This again shows the logarithm of the density. And this is a radial slice of one of our simulations. So R is equal to constant. And the pole is right here. You can see some numerical artifacts associated with the pole. and the equator runs around here. This is a negative spin model, which is in our language means that the accretion flow is going one way and the black hole is going the other way. So it's a retrograde accretion flow. And we let it go, and you can see the disk circulating around the black hole. So this sense of rotation is set by the boundary conditions at large distance. And then you can see over the poles, there's not much here. Any plasma that was there has fallen into the black hole or been expelled to large distance. And you can see that what plasma there is rotating in the opposite direction. So these field lines are being frame dragged by the rotation of the black hole. So this is the Blandford-Znajek effect, and again, the time averaging matches Blandford-Znajek's monopole solution. So what predictions does Blandford-Znajek make for the origin of jets like the one that we see in M87? So the first prediction is kind of a low bar. There's a black hole at the base of the jet. I don't think anyone has seriously doubted this since the 1990s, but we'll get to that in a moment. Another prediction is that the black hole is indeed spinning. And to check this, we need to devise a way of measuring the spin of the black hole. A third prediction has to do with the magnetic field geometry close to the hole. There should be this trailing spiral configuration that I described earlier. And then finally, one wants to show that the power in the jet matches the power predicted by Blandford-Znajek. Okay, so there is a black hole at the base of M87's jet. I don't want to belabor this point. This is the image of a black hole from 2019. It's still there a year later. It's certainly reassuring. And it seems to lie at the foot of the jet in M87. So this represents a tremendous amount of effort over many years by many people. So this shows a series of sort of zoom-ins on the base of the jet in M87. This is the GMVA image. So this is a 3.5 millimeter image, 86 gigahertz. And you can see there's a core there and there's something near it. And then this is the EHT image, which is higher frequency, 230 gigahertz, and therefore higher resolution. Recently, there was a paper by Liu et al. Looking at more data from the GMVA, looking at 3 millimeter data. And here you can see both the core, which seems to have a little dimple in it, and a direct connection to the jet. So I think this, pretty persuasively makes the case for the first prediction. The next prediction is that the black hole is spinning, and this is somewhat harder to test. One would like some kind of direct measurement of the spin of the black hole. So in the analysis of EHT data, one thing we did was compare the images that had come from EHT to synthetic images from models based on simulations like the one I showed you. The GRMHD model comparison suggested that the spin was greater than about 0.5. But this is based on a somewhat circular argument. And the argument is that you have to produce enough power to match the broad range of observed powers seen in M87's jet. So this is certainly consistent, but not the end of the story. So let me just show you. Okay, so this is our model comparison. I think someone showed galaxies, so I felt I had to show this zoo of MHD simulations accreting black holes. You can see that some of these are different. They don't all work as explanations for what's going on in M87. Okay, so there are many ideas for using EHT data to measure the spin of M87. And there's a nice review by Angelo Ricarte, who's a postdoc here now in the BHI. And one of the most straightforward ideas is to directly measure the radius of the lensing ring around the black hole. So it turns out that the radius of this lensing ring, which is a sharp feature in the image, does depend on spin, but it depends very, very weakly on spin. So the first order correction is proportional to the square of the spin divided by 18. So it's probably quite small. So it's really hard to measure from the ground. And so you probably need to go to space to put an EHT antenna in space to gain extra resolution. And this hopefully will be done by BEX, which is the Black Hole Explorer proposal, which is PI'd by Michael Johnson here. Unfortunately, this needs not only an antenna in space, but it also needs a precise independent measurement of the black hole mass to understand what the correction is. So very difficult to apply to M87. There are lots of other ideas. So I'm gonna mention two from my group, which are based on movies of M87, which is something that we expect to see from Event Horizon Telescope or next generation Event Horizon Telescope fairly soon. So the notion is that the ring has fluctuations in brightness around it, and that these brightness fluctuations circulate. And the rate at which they circulate depends on the spin. So these fluctuations have a pattern speed, and that depends on the spin, and you can extract that pattern speed by revisiting M87 a sufficient number of times to make a movie. Another possibility is to look at the pitch angle of spiral features in the accretion flow. So that means taking a movie and comparing, cross-correlating the brightness fluctuations at different radii, and then using that to measure the pitch angle. The notion there is that for high-spin black holes, the spiral waves in the accretion flow are more tightly wound, which I think is intuitive and unsurprising. All right. So I'm just about to wind up. Let me say that again that there are lots of avenues for measuring spin. One, I think, that hasn't really been fully explored so far is how the amplitude of the asymmetry in the ring. So let me just quickly go back to the image. So there's an asymmetry in the ring here. And it's not clear, or hasn't been clear, how that asymmetry depends on spin. And we've now been able to measure this by doing a more exhaustive spin survey than was possible before. And for each model, the magnitude of the asymmetry fluctuates in time. And so you have to compare the distribution of observed asymmetries in a movie to the expected values from a simulation. And you have to believe the simulations. Okay, so I'm going to wind things up and wind up the conference, except for remarks by Avi. So black hole energy extraction is a fundamental process in gravitational physics and almost certainly in astrophysics. It almost certainly drives the extragalactic radio jets. Blandford-Znajek makes a few predictions. So some of these have been tested. I think a direct measurement of black hole spin is next through some combination of data from EHT or next generation Event Horizon Telescope movies or movies taken with the Black Hole Explorer. There are also ideas about looking for the field geometry in the polarization data. So Andrew Shale has pursued this recently in collaboration with a few others. And finally, one wants to check that the jet power matches that expected from BZ, and there aren't a lot of ideas for doing that. That's a very, very hard problem. Okay, that's it. Thanks.
So we can take questions. Shmadar.
Thank you. What can you say about the spin of our own galactic center supermassive black hole, and does the variability that you observe there through EHT helps or not helping at all with measurements of the disk, of course?
Yeah, so we don't know an awful lot about the spin of the Sagittarius A star yet. So there was a model comparison exercise done there that does seem to favor spinning black holes, but it's I think because the models work less well for the galactic center, it's less clear what's going on. I think your second question was related to this so-called variability crisis. So just to briefly recap, in the millimeter light curve of the galactic center shows sort of 7 to 10% variability over the course of a few-hour integration. And the models that work best for the EHT observations tend to show larger variability than that. So there are a lot of ideas for repairing this variability crisis. So one is to look at non-ideal models that incorporate kinetic effects. And I have a student who's doing that. They do, non-ideal models do seem to show somewhat lower variability. The second idea has to do with the observations themselves. So it may be that there's extended, slowly varying structure in between the scales that can be resolved by EHT and scales that can be resolved by connected element interferometers. And so those would change the sort of denominator in the statistic that we're using to test the models. So it looks at the fractional variability. So if our estimate of the total flux is too large, then that will be too small. So it could be a problem with the observations, could be a problem with the fluid models themselves.
Thank you.
Actually, I'm going to take advantage of being up here. So the actual observed jet coming out of M87 is very collimated, very narrowly collimated. And I never see that degree of collimation in the models. Is that a source of concern?
Well, the models, so I think ultimately collimation depends in part on the external medium. And the constraints there are a little bit less clear. I would say that if you look at where's Roussen's image? If you look at this image, it's not very collimated close to the source. So this extends, so remember this jet is tilted at sort of 20 degrees to our line of sight. So we're looking at a region that covers, hundreds to thousands of GM over C squared away from the hole. And you can see that it's not very well collimated in this region. And this is really the region that we can model most reliably in M87.
Okay, because I'm good-natured, I'm going to have one last question.
Thank you for an excellent talk. I do have a question. There are evidence for weaker jets in systems that contains only neutron stars, not black holes, namely no event horizon. And I was wondering whether, to your opinion, it's the same mechanism, the same Blandford-Znajek, or there'll be something else that produces the jets that we see.
Yeah, and of course there are jets in protostellar systems as well. So the notion is, what's so special about black holes? And I think the answer to that is nothing. In all these systems, there's a rotating object in the center, which anchors the magnetic field. And it produces a wind that has a speed of order the escape speed. So from protostars, it's a few hundred kilometers per second. From black holes, it's close to the speed of light. And in the black hole case in particular, the jet is cleaned out close to the source by plasma falling down the field lines into the event horizon. And so you really have a system which is well designed to produce a highly relativistic outflow. But the answer there is nothing. It's not different.
Let's thank all of our speakers. Again, it's been a great series.